Here's another example of how to do a projectile motion problem. Let's read the problem and see what it's all about. A basketball player attempts to make a basket from a distance of 8 meters. The basket is 3 meters high and the ball leaves her hands from a height of 1 meter. If she throws the ball at an angle of 45 degrees, what does the initial velocity of the ball need to be? All right, usually a problem like this strikes the fear into a lot of students. It used to for me as well. Wow, how do you start a problem like this? Where do you begin? Well, it's not a bad idea to begin by writing down all the things that are given, so let's go find them. It says here that the distance to the basket is 8 meters, so we can say x equals 8.00 meters. The basket is 3 meters high, so y or h is equal to 3.00 meters. So we're given this. The ball leaves her hands from a height of 1 meter, so that would be the initial height. The starting height would be 1.00 meters, and she throws the ball at an angle of 45 degrees, so we have this one. Now we go over here, we say the angle theta is equal to 45 degrees, and finally they say what should be the initial velocity to attain that basket, so v initial equals question mark. That's what's being asked. All right, so we have a pretty good idea now what's given and what they're asking for. But again, in order to really feel what we need to do here, try to figure out what we need to do, we want to make a nice little graph or drawing of what's happening. So here's our basketball player throwing the basketball at an angle of 45 degrees. Theta equals 45 degrees with some initial velocity, which we don't know. That's what they're asking for. All right. The basketball will move in a parabolic path, and we're trying to hit the basket. The basket has a height of 3 meters. That's the final height, the y right there. And they also tell us that the basket is 8 meters away. X equals 8 meters away. Like so. Okay, that gives us a much better feel for what's happening. Here's a basketball player shooting the basket, or shooting the ball to the basket, right there. Supposed to hit the basket, 8 meters away, basket's 3 meters high. The ball leaves the hands of the player at a height of 1 meter, so y initial equals 1 meter. This would be h, or y equals 3.00 meters. Y would be the final height. All right, what's next? What's the strategy? We need a good strategy. And I would say projectile motion, time in the air, probably not a bad way to start. Time in the air. Now, since we're given the distance, I'm going to use the horizontal component of the velocity to find time in the air. Oh, but I don't have the horizontal component yet, so let's do that next. We need the horizontal component of the initial velocity and the vertical component of the initial velocity. So v initial in the x direction is equal to v initial times d, since the component is adjacent to the angle, times the cosine of theta. And over here for the vertical component, v initial in the y direction is equal to v initial times the sine of theta. Plugging in what those are, so it's equal to, oh, we don't know what that is. That's v initial times the cosine of 45 degrees, and the cosine of 45 degrees is 0.707, so we can say that this is equal to 0.707 v initial. And since it's exactly the same for the sine of theta, because at the angle of 45 degrees the sine and the cosine are exactly the same, we can say that this is equal to 0.707 times v initial. All right, so now that we've expressed the velocity initial for the x and the y component, we can calculate the time in the air. So we can say that x equals x sub naught plus v sub naught in the x direction times time plus 1/2 at squared. That's our equation of kinematics that we have right up here. Notice that in the horizontal direction, the moment the ball leaves the player's hand, there's no forces involved, so there's no acceleration in the x direction, so that's 0. We can assume that the initial position, x equals 0, at time equals 0. So this equation becomes x equals v initial in the x direction times time. If I now plug in everything that we know, or well, let's solve for time first. Let's say time is equal to x divided by v initial in the x direction. I simply divide both sides of the equation by v initial in the x direction. And so that means that a distance of 8 meters divided by v initial in the x direction, which is 0.707 times v initial. So here I have now expressed the time in the air in terms of the initial velocity. If I now plug this into my second equation of kinematics for the vertical component, I'm now going to grab my second equation right here, which is y equals y sub naught plus v sub naught in the y direction times time plus 1/2 gt squared. Remember, in the vertical direction, since there's gravity, we have an acceleration due to gravity g, which is a minus 9.8 meters per second squared. I am now going to plug this value for t both in here and in here. When I do that, I get the following. Final height, 3 meters. Initial height, 1 meter. I'll put parentheses around it so it's a little cleaner. Plus the initial velocity in the y direction. Now the initial velocity in the y direction we have over here, which is 0.707 times the initial velocity, multiplied times the time, which I have over here in terms of v initial. So it would be 8.00 meters divided by 0.707 v initial. All right. Now, I still have a plus 1/2 times g, which is minus 9.8 meters per second squared, times the time squared, and the time is over here, so I plug that in, 8.00 meters divided by 0.707 v initial, and the whole thing is squared. All right. Now notice I now end up with one single equation that only has a single unknown in it, v initial, and nicely here, this 0.707 v initial cancels out with this 0.707 v initial. So now I have a 3 meters equals 1 meter, and then plus 8 meters, so I can move everything over to one side, and I have a 3.00 meters minus 1.00 meters when I bring this one across. And what I have left over here is a minus 8.00 meters when I bring it to the other side of the equation, equals 1/2 times 9.8 is a minus 4.9 meters per second squared. And multiplied times 8 squared, which is 64.0 meters squared, divided by this number squared is 0.5 times v initial squared. Okay, so I squared this term right here, which is 64.707 squared is 0.5, v initial squared is v squared, and then 1/2 times 9.8 is minus 4.9. Combining what's on the left side, I have a 3 minus 1 is 2 minus 8 is a minus 6.00 meters equals minus 4.9 meters per second squared times 64 divided by 0.5 is 128, so that's 128 meters squared divided by v initial squared. Okay, now I'm ready. I have a negative on both sides. I can multiply both sides by a -1 and make that positive. I can now move the v initial squared over here and the 6 meters down here. So let me move over here so I have a little bit more room. So I'm moving my v initial squared to the other side, diagonally across. I have v initial squared is equal to, I still have a 4.9 meters per second squared. I still have 128 meters squared, and now if I bring the 6 meters across over here, divide both sides by 6 meters, I get 6.00 meters. Okay, so this meter cancels out this meter, and I have a meter squared and a second squared, and I have v initial squared on that side, so I can take the square root of both sides. So v initial is equal to the square root of 4.9 times 1 over second squared times 128, that's meters squared, all divided by 6.00, And now let me grab my calculator. Okay, 128 times 4.9 divided by 6, and take the square root of that. I get 10.22 meters, or the initial equals 10.2 meters. That should be the initial velocity of the basketball if she has any aspirations to hit that basket. And, yes, I forgot something. Thank you. Meters per second. Yeah, velocity in terms of meters wouldn't be very good, would it? 10.2 meters per second.